An organic compound I is analysed using a combination of techniques. The analytical data is shown below. Elemental analysis by mass: carbon is 56.69%, hydrogen 7.09%, nitrogen 11.02%, and oxygen is 25.20%. The mass spectrum molecular ion peak is at an MZ value of 127.0. We don't have the IR spectrum, but we do have the proton NMR spectrum. Part A. Explain the use of two deuterated compounds in NMR spectroscopy. The first use of a deuterated compound is as a solvent. Chloroform D, which is CdCl3, is a really common solvent in NMR spectroscopy. The second use of a deuterated compound is D2O, which is used to identify OH or NH peaks, because using D2O will get rid of these OH or NH peaks when they would be there if D2O wasn't present. To get the 2 marks for this question, you get a mark for talking about chloroform D being used as a solvent, and then you get a mark for D2O being used to identify OH or NH peaks. Part B. Determine the structure of compound I, showing all your reasoning. So the first thing to do when you get a question like this is to work out the empirical and the molecular formula. And we do this using the elemental analysis by mass. So starting with carbon, we do 56.69 divided by 12, and that equals 4.72. Then moving on to hydrogen, we have 7.09 divided by 1, which equals 7.09. Then nitrogen is 11.02 divided by 14, which equals 0.787. And finally, oxygen, 25.2 divided by 16 equals 1.575. Then we divide by the smallest number, which is nitrogen's 0.787. So dividing everything by 0.787, for nitrogen we get 1, for oxygen we're going to get 2, so dividing by 0.787 equals 2. For hydrogen, if we divide by 0.787, we get 9. And finally, carbon, dividing by 0.787, we get 6. So our empirical formula is C6H9NO2. Then we need to work out the molecular formula, and we do that using the molecular ion peak, which is going to be at 127. So that is the relative formula mass of our compound. So if we work out the relative formula mass of our empirical formula, we can either scale up or keep it the same. You can't scale down because empirical formula is the simplest way to write the molecular formula of a compound. So we do 12 times 6 plus 9 plus 14 plus 16 times 2, which equals 127.0. So we keep it the same. This is going to be our molecular formula and our empirical formula, which means that the molecular formula is the simplest way to write it. Then we're going to start looking at our spectrums. So we don't have the IR spectrum, but we do have the proton NMR spectrum. So this peak has a chemical shift value of 2.9 ppm, and it has a quartet splitting pattern also because there are 4 lines in the peak. But there's only 1 hydrogen in this environment. So 2.9 ppm is when you have a carbon double bond oxygen connected to a carbon with a hydrogen. So that's the chemical shift value for this specific group, which you can find out on your data sheet. But we want a quartet splitting pattern, so we want this hydrogen in the middle connected to CH3, because for each of these peaks, the carbon in question we're looking at is the middle one. So then moving on to when we have the first integration of 3. So this has a chemical shift value of 1.7 ppm, and it has a doublet splitting pattern because there's only 2 lines in this peak. and there are 3 hydrogens present. So this is the chemical shift value for when you have R and then CH. So it's just an alkyl group that the carbon hydrogen is connected to. So if we have CH and we want a doublet, but we have 3 hydrogens, so the hydrogens we're looking at are these 3, and by connecting it to a carbon with 1 hydrogen, that means we're going to produce a doublet splitting pattern. Finally, the last peak on the proton NMR also has an integration value of 3. It has a chemical shift value of 1.3 ppm, and it has a triplet splitting pattern, which means it'll be connected to 2 hydrogens. And then finally, there are 3 hydrogens because of the integration value of 3. So it's going to be CH3, CH2. And again, we're looking at this CH3 part because of the 3 hydrogens shown by the integration value, but we want a triplet splitting pattern, so we need to be next to 2 hydrogens, and because it's still in the range of RCH, so it's an alkyl group we're going to be connected to, we just need to have 2 hydrogens in our alkyl group, which is CH2. So we haven't yet thought about nitrogen. Looking at the proton NMR spectrum, we can see that there are no NH peaks, it's not in the NH range, and it's not in the amide range, which is C double bond O NH. So we know that the form our nitrogen is going to take is in a nitrile functional group, so C triple bonded to a nitrogen. Because we can't also have another proton environment, we can't have any more hydrogens because we've only got these 4 environments shown in our NMR spectrum. So if we start by drawing our first structure, that is just going to be putting together all of these different groups that we've identified using the proton NMR spectrum. So we're going to have CH3, CH2, O, and then we're going to have C double bond oxygen, CH, CH3, and then this is the perfect place for our nitrile group to go, or our CN group. And then we can double check that we've got our 4 proton environments and they're all correct. So if we look at this first one here, we have got our first proton environment, our quartet splitting pattern with a chemical shift value of 4.2 because it's connected to this oxygen. Then if we move along and we look at this one, well, we have our proton environment here from our hydrogen. It's connected to this carbon double bond oxygen, and it will have a quartet splitting pattern because of this CH3 group. And then our 2 alkyl groups with the splitting patterns of 1.7 ppm and 1.3 ppm are shown because we have them here. That's our first one with a chemical shift value of 1.3 ppm, and then our second one with the CH3 is here in a kind of L shape at the end of our compound. So this is our first possible structure, but there's more than one answer for this question. So our next possible structure is CH3CH2O, so same to start with, but then we have our CH and CH3 group in the middle with our carbon double bond oxygen and our nitrile group at the end. So again, we are going to check our proton environments. So our 4.2 proton environment is shown here. This is going to be the hydrogen that creates this quartet. It's connected to a CH3, so it will have a quartet splitting pattern, and it's going to have a chemical shift value of 4.2 because of this oxygen that it's bonded to. Then if we look at our 2.9 ppm proton environment, so that's going to be this hydrogen here. Now it's still bonded to the carbon double bond oxygen. It's still going to be a quartet because of this CH3 group. So again, we've corrected and we've checked that we've got both proton environments. The 2 RCH groups Well, they are also represented. We have our first one here, and then we have our last one here, where we have the CH3CH2, and then we have our CH3. So again, this is a very correct, another possible structure that we could have for this question. The last part of this question is to confirm the functional groups. So we have a carbonyl and a nitrile functional groups in our two compounds, and these are the two possible compound I's based on the data we've been given. Now, even though we don't have the IR spectrum, we were able to work backwards and find out that we need to have a carbonyl group to have the correct proton environment chemical shift value. And because if there was an NH something, so an amide or an amine, that would show up in the proton NMR spectrum. And there are only 4 proton environments, so we can't have an amine or an amide. We have to have this nitrile functional group. Because this is a level response question, there aren't specific marking points. Instead, to get the 6 marks, your structure of I has to have a viable chemical structure of C6H9NO2. So that's the molecular formula that we carried out. And it needs to have the key features which are consistent with the spectral data. So the carbonyl and the nitrile functional groups, and also making sure that your proton environments are correct and they match up with the spectra. Also, you need to have most of the data analysed. So that works out because we don't have the IR spectrum, so we haven't been able to analyse the IR spectrum, but we have analysed every other bit of data, so that's most of the data analysed.